Hello. Now we are going to talk about regression evaluation matrices. So now, so in the last lecture, we did discussed about how to evaluate the classification model, right? Now we'll talk about how to evaluate the regression models, right? So we have a different matrices for the classification. We have the different matrices for the regressions, right? Now we'll talk about that. So first, we'll download our data set. So here we'll be using the Kaggle data sets, right? We have splitted our data into training and testing. After that, again, here in this data, the sales price is our Y value, which is the numerical. Now, because the sales price is the numerical, so this is a regression problem now, right? So our Y value is the continuous, so it's a regression problem now. Now here, when we check the shape of the data, it's like the 1300 number of examples we have. First, we need to separate X and the Y for both training and testing. So here we are separating the X part of the data and the Y part of the data for both training data and the test data as well. Now, as now for the EDA, we can simply do a describe. Basically, this will give you the number of counts is there or not. Do we have missing value? You can get with the count. We can check the mean value. So the mean value is getting like here. The mean value of all the column is very different, right? We can check the standard deviation, we can check the minimum value and the maximum value, right? So it's a very varying, right? Now when we check the info, basically this will give me the introduction about the columns, like which column belongs to or like which data type, right? Here we can see that, like here we can see we have some missing value in the lot frontage. We have the like missing value in the alley, right? We have the missing value in this mass variable type, right? So we have some missing value over here. We can see that, right? Now, there is a tool called Panda Profiler, right? So basically, this Panda Profiler will help you to profile all the data in just one go. Again, for that, you need to install it. For the Conda installation, we can simply do the Conda install Conda Force Pandas Profiler. This will install our our Panda Profiler into the Anaconda package, right? And now you need to run this code. Now, here, now because this will take a lot of time, right? So we are not running the code over here, but again, when you get the code, you can install this Panda Profiler and then you can run the code. Now, when we look at the features, right? We know that, like again, when you look at the information from the Panda Profiler, which is not here, we are not running it, but once you look at that, right? Because this Panda Profiler is the automated tool, right? We should not blindly trust all the data because this Panda Profiler work if the data type is categorical or the discrete, it will be considered as a discrete. But if it is labeled as a numeric, so it will consider as a numeric data type. So it's not very much smart. We have to be like, because it is the automated tool, so we should not blindly trust it, right? Yeah. Now you can also look at the data descriptions at here, which is the, because we have downloaded the data from the Kaggle. If you want to check the description of the data, you can click on the link and then you can see the basics data descriptions, right? Now let's talk about the feature types. Now in this data, we have the mixed feature types, right? And also we have the missing value. We have already discussed about that, right? So what we want is we want to create a different type of transformer for the different type of data types, right? So first we are selecting the numeric looking columns. So with this code, we are extracting all the numeric looking columns. Now, now not all numeric looking columns are the numeric. So when we look at this MS subclass, so MS subclass is labeled as a 20, 50, 30, 60, 160, and so on. But this is the unique value we have, right? Now, this looks like a number, like numbers, but it is not a number. It's a category. It's a label given in a data, right? Just for the simplicity. And here is the label means. So if we see 20, this means that one story, 1946, on and newer all styles. 30 means one story, 1945 and older. 40 means one story, well finished, attic, all ages, right? So we have a different category for the different data, right? So here, though it looks like a, so the all the value inside a column is integer, it is not a integer data type. So it is not a numeric data type. This column belongs to the categorical data types. Okay. Now we can also look at the month sold. So we can see the month sold is the all the value between 1 to 12. Basically, this is the number of month, like Jan, Feb, March, right? And here we also have the ID. Now we should drop the ID because ID is just the unique value, right? It's a nominal data. We cannot use the usage. We cannot have the usage of the nominal data in the Brazilian domain, right? So we can drop it. Now here we are extracting all the numeric features, right? So now, like using this code, we can look at that, and here we have extracted all the numeric features, which are the numeric value. Now, because we have the numeric feature, now what we can do is we can uh, we can subtract the numeric feature from the numeric looking features, right? And also we'll kind of subtract the drop value, which is the ID. Now we have the two features, MS subclass and MO sold. Now these two examples, this MS subclass and month sold, looks like a numeric feature, but in reality it is a categorical data, right? All this will be used, all this will be defined during the data explorations, right? So when we do EDA, all these things we can, like all these things we have to be, make sure that to identify and to find the issue with the data, right? So that later on you do not need to do that, right? And the machine learning building process will be smooth, right? Now here, now we'll treat all the columns as a numeric columns over here, right? Now here, we also have the ordinal feature as well in the data set. Now the ordinal feature with the same scales we have, right? So we know that, like, so here we have the ordinal feature as a scale of poor. Poor is the ordinal value, then again fair, typical, good, excellent. These are the ordinal features we have, right? So poor can be labeled as 1, fair can be labeled as 2, typical can be labeled as 3, good will be labeled as 4, and the excellent will be labeled as 4, right? So excellent will be labeled as 5. This is our ordinal feature with the same scales, right? For that we can create a new new columns, and then we can assign all these features, right? And we also have the different ordinal feature with the different scales, right? Now here we are we are storing all the feature which is ordinal with the same scale, right? With the like with this regular scale, and here we are storing all the columns. Now this is the ordering that we are setting. So this is the order we have for all the, so now all this column has the order of poor, fair, typical, good, excellent. All this column has the same ordering. Now how do I know? I know because during the data exploration you will identify this, right? Now we have this ordinal feature regular. So here we have, right? So here we have this ordinal feature regular for all the columns, right? So this is for the first column, second column, third column, like, yeah, so third column, fourth column, and so on. Now we'll pass the above as a category in as an ordinal encoder. So we can pass this. Now now there are a bunch of other ordinal features which have the different scales, which are not on the same scale. We can use this, and we are storing that feature in the ordinal feature others, right? And we can encode them separately. So here we have these features, all these features, these are the ordinal feature, and they have the different ordering for those for, so for all the feature we have the different ordering, and here we are encoding all this, right? Now, so now we have separated our ordinal feature, we have separated our numeric features. Now the remaining will be the categorical features. So here we are trying to extract all the categorical features. Now these columns belongs to our categorical features, right? So now, by now we have separated our columns. We have separated all the different type of columns in our data, right? Now our task is to build a different preprocessor related to different type of data, right? So that we can apply it into a machine learning task, right? Here we are applying a feature transformation. So here we'll be using the column transformer, right? So first we are making a numeric transformer. Then again, this ordinal feature, ordinal transformer for regular, ordinal transformer for others, categorical transformers, right? And after that, we are combining all these transformer, right, with again a new transformers, right, and assigning our all the columns and this, and we call this as a preprocessors. So this is our preprocessor now. So now we have created a preprocessor which is able to detect a specific type of column, do a pre-processing task, right? It will kind of identify all the columns, and based on that, it will do it will apply the pre-processing steps, right? Now we can simply apply the fit method. We can call the named transformer. This will give you all the transformer related to every task, right? So here we had applied the fit method. We can also extract, like here we are extracting all the column names, right? And like all the new names that we are extracting, and here because we have, when we apply the fit method, right, we can apply the transform, right? Here after the fit we are applying the transform, and then we are trying to look at the transformed data. So this is our transformed data now, right? So now what we have done, now we have made our model such that, like, now we have transformed our data such that, so that we can use our machine learning model, or now we can build a machine learning model. So here we have here we have created our data, right? Now now we can check the shape of the data before transformation, and after the transformation the shape of the data has changed. So now earlier we had only the 80 columns, but now we have 263 columns. So we have increased the number of features, right? Now what other possible pre-processing that we can apply? We have just used the simple imputer. Instead of that, we can do the ED, and then we can do sophisticated transformer or sophisticated implementations, right? Of course we can do a lot more, right? But our purpose is not to understand the transformer or a preprocessor. Our purpose is to understand the regression based evaluation matrices, right? Now first, now let's talk about the model building part. Now now we have built the preprocessor. Now let's build our models, right? So here first we are building our dummy regressor, right? And here we are using a cross validate functions on the dummy regressors, right? And now the value we are getting as a test score, we are getting the 0, as a trend score as a 0. Now again, remember that this dummy regressor in the score function, it uses R2 score. So now this R2 score, if you are getting the 0 value as an R2 score, this means that your model is 50% accurate. So your model is being random, like giving a random output, right? So again, this R2 score have the highest score of 1, but it can go to the minus infinity, right? So 0 means now we are getting a 50% accurate model, right? Now we can apply the ridge regressions instead of linear one. We have already discussed about this. So ridge has this alpha hyperparameter which controls the fundamental trade-off, right? Now here we are making a pipeline with the preprocessor to the ridge regression, and now we are passing to the cross-validate functions. Again, in the cross-validate function, we have this test score and the train score. Now using the ridge regression, now we can see that our training score, mostly all the value that we are getting is approx 90%, right? And our test score, also we are getting most of the model we are getting as an close to 85%, and only the one model, which is this model 8, right? We are this ninth time cross validation, we are getting only 19% of the correctness in the validation data. Again, this can be possible because of the random chance, right? Now, now let's tune the hyperparameter for the ridge regression. Now, just like the C hyperparameter is there for the logistic regression, same as we can tune this alpha hyperparameter. Right, so here we are passing this multiple value of alpha. We have created this train score and the CV score list so that we can store the result for the training and the cross validation. For every value of alpha, we are making a pipeline over here, and this pipeline is being passed to the cross validation, and then we are storing the like here we are storing the mean of the results, right? And the cross validation mean of the results, right? So and like test score mean value and the train score mean value, right? So and after storing all the result for the different value of alpha, here we can see the result in the graph. We can see that. So this alpha value was from like 10 raised to minus 4 to 10 raised to 2 to 10 raised to 2, right? And like so we have taken the value from 10 raised to 5 to 10 raised to 4, right? And here we can check the score value. So this is the score value for the like this is how the progress for the training data. This is how for the like this is how the progress of the cross validation data. Basically, we need a model where we want the highest cross validation score, right? We can simply look at the argmax and then we can see that like alpha value as in 100. So here we can also look at this. So at 10 raised to 2 we have the highest cross validation score. So we can check this. So this alpha value, which is the 100, can be the best alpha value, like it can be the best hyperparameter, right? And then we can use this hyperparameter to retrain our model, right? So here now Now here first we are building a pipeline with the ridge regression, and then we are also using the cross validation in that. Now you do not need to create a separate model for the cross validation. Instead of that, you can use the ridge CV. What this ridge CV does, basically it's a way to tune the alpha value with the ridge regression. And then when we have this ridge CV, this CV stand for the cross validations, right? So it will do cross validation and the parameter tuning as well, right? So we just need to create a pipeline. Here in the ridge CV we are passing alpha value and then we are passing the CV as a 10. Basically it will do this 10 type cross validation score. Then when we apply the fit method, here we can check the best score, like the best alpha. Again, using the ridge CV also we are getting the best alpha value as 100, right? Now, what we'll do, now we'll recreate our model with the best alpha. So here we are again making a pipeline with the best alpha value of the ridge regression, and then we are applying fit and the predict method. So this is the exit value that we have got, right? And here we can see that the maximum value is this for the prediction and the minimum value is this for the predictions, right? So now we have trained the model. Now let's get our feature name for the transformed data. So here we have created a new columns and after that, here we are trying to look at the coefficient value of the of every columns, right? So here we can see that. So we have these features, we have this coefficient value, right? So every feature have the associated coefficient value, and basically we have done we have yeah. So here we have sorted our data frame uh, in a descending order, right? When we say ascending is false, it will be in the descending order. So this overall coil has the highest coefficient. That means this column impact high on the model. Then this column, and so on, and which makes the lowest impact. Again, so lowest. So again, this neighborhood advert is also making the highest impact, but it is in the lowest direction. We cannot say it's a lowest. It is also making like it is also making the impact to the model, but this is making into the negative sense, right? We also have the model which where the coefficient value, like we also have the column where the coefficient value would be 0 or close to 0, right? Those column will make the lowest impact to the model, right? So now according to this we can see that this overall quell, if this feature gets bigger, that means it will impact more onto the model, right? So if this overall coil feature gets bigger, the house price will get bigger, and the neighborhood advert, if there is a neighborhood advert as an as a neighborhood around the house, right? Then their result will slightly decrease. So then their house price will slightly decrease. And this is what we can understand with these features, right? We can also look at this, what is happen in like what is there in the neighborhood hardware, right? And so on, right? Now we have built the models, right? Now let's talk about the regression score functions. So we have already built models. We have trained our models. Now let's try to predict the value and try to check with the y, like y train. So here, this is the predicted output that we are getting and try to check with the y train. And here we are using this equal to. So just like the classification, right? In the classifications, we do the hard predictions and the model always predict whether the class belongs to, like whether this example belong to class A and the B, right? And then when we check with the equal to, basically we get the, like if the model has predicted correctly, so we get the correct, like the true output. But here in this case, in case of regression, now it doesn't matter how good you build a model, this equivalent is never going to be the true. Like all the examples will be false. Why? Because this is the numerical value, right? So to evaluate the numerical value, right? So even the value with the 0.1 and the 0.2 differences, right, will get the value as it false, right? So it has to be exact the same value to be a true, right? Which is never going to be same, but model will predict you the approximate value, right? And like close to the predicted value, right? If it is a good model. So we'll get always false when we check the values of the y train, and when we check the values of the predicted. Here we can see that we have got a close value, but not the exact what is there with the actual y value. So we need a different score functions, right? We need to score that reflect how good each prediction is. And then the popular scoring functions are there for the regression problems. So now these functions are the mean square error. Sometimes, like we also call this as an MSC. We have this R2 score. We have this root mean square error. We call this as an RMSE. And then we have this MAPE. This is called mean absolute percentage error, right? Now we'll start with the mean square error. Now, what is this mean square error? Basically, it's a error of like, so it's a mean of square of the error. So first we take the error. So here we have stored our predicted value into the pred. First we have taken the difference. When you take the difference between actual value minus predicted actual value and the predicted value, you will get the difference. After that, you will have to take the square of that difference. So when you do the square, basically, even though if you'll get the, like even though if with while checking the difference, if you get the like if you get the negative value, right, that value will be that value will be removed when we'll take the square of it, right? And after that we'll take the mean of it, right? So here we are getting the error as on this much, which looks very big, right? Now what is the ideal error should be? So ideal error should be 0. So we want a model which has to be exact equal to the predicted value, which is never going to be true. Like, so this ideal MSC is never going to be true, but we can, but again, we can have a small differences, right? But not this much big error. We do not want this much big error over here, right? And here we can also check with the ideal error. We can check with the with the actual value and the actual value. We can see that we have got the 0 value over here. We can also implement it. We do not have to implement everything from scratch. We can also import this mean square error function, this mean square error function, right? And we can pass this actual and the predicted value. We'll get the similar result. Now, this result we are getting as a huge, right? So the question is, like here we have the error as an approximate of 1 billion, right? So the question is this a good score or bad score, right? By looking at the result, it looks like it's a very big error that we are getting, right? So in classifications, like unlike classification here, our target has a unit. Like classification does not have any unit, but here we have the unit. And this output that we have got, this error we have got as in the dollar square. Why? because when we did the mean squared error, so when we took the square value, we have doubled down the value. So that's the reason we have the unit of the double dollar square. Now, this course also depend on the scale of the target, right? So what is the target scale value we have, right? And now again, like if the scale of the target value increases, this value will also increase, right? Like over here, consider that we are kind of converting our dollar to a cents. Like let's say that if uh, instead of dollar, if we have the cents, right? So if you convert this value into a cents, right, and like when you check the output, it is even a lot bigger, right? So that means if the target unit changes, the value also changes. So when we look at the error, we have to look the error in terms of the unit, right? Then only it will make sense. Now let's try the root mean squared error. So here now we have already tried the mean square error, right? Now for the root mean square error, we just need to take the square root of the mean square error. And here, when we look at this root mean squared error, so what we get? We get the error of approximately 30,000. Now we have the error of 30,000. So now this makes sense, right? So again, like $30,000 of the error we are getting. Like so, with the every prediction, like let's say that whatever the model has predicted for the house price, we can have the error of $30,000, right? Now the question is, can we dig deeper? Now again, for that we can just predict, like we can plot our model over here, and here this is our model, this is our actual data, right? And what we see over here is most of the data are aligned with the model, but there are few data which is far away from the model. Maybe because of this data only we are getting the error, right? Like over here, maybe we are getting huge error because of these two data. Maybe we are getting huge error with these two data. Like over here, we can see that our true value, right? Our true value is around here, but our predicted value here, our true value is around 2 lakh, but our predicted value is around 5 lakh or 6 lakh, right? Which is very huge, right? Maybe this example is a special example. If you can look at this examples very closely, then we'll understand, right? Why like why this example behave in this way. Like over here as well, the actual value of the model is like the according to the like data, our actual value is 70 lakh, right? 7 lakh, right? But the predicted value is approximately 4 lakh, which is a very different, right? So maybe because of the few examples, our model is making big mistake, right? Maybe this example is an outlier. So what we can do is we can remove these examples, right? Or you can kind of check the data, or you can transform the data, right? This is what we can do. Now, now we know what are the tips, what are the techniques that we can apply, right? Now let's check R2 score. So again, we'll not talk about R2 score in more detail, right? But again, consider that this is the common, uh, uh, like uh, this is a common matrix for the regression. So when we call the score function from the regression model, it call the R2 score function only, right? You can read it out, like you can check out this link to understand about the R2 score, right? Again, the intuition is it is similar to the mean square only, right? This mean square error only, but it is flipped. That means higher is better, where the mean square error is lower is better, right? So if the mean square error we are getting 0, that means we have got the good model. But in terms of R2 score, if we have got higher value, then it is a good model, right? And this is normalized and max to 1. That means when you got the R2 score as an 1 value, that means you have got the best model, right? If you have got the 0 value, that means it is a dummy regressor output, or it is a model with the 50% accuracy, right? And if you have got the negative value of the R2 score, so in the R2 score, it is possible to get the negative value, right? So if you have got the negative value of the R2 score, right, that means you are doing worse than the dummy regressor, right? And it can go up to the negative infinity. This is how R2 score work. Now let's talk about MSC, like how to use this MSC and R2 score, right? So when we apply the MSC, or when we try to try to create this mean square error, we can pass actual data and predicted data, and we can even flip this predicted data and the actual data. Like here we are changing the placeholder for both training and the predicted. For both, we are getting the correct output, but in terms of R2 score, we are getting the different output. Here first we pass the actual data, then the predicted data, and then we are getting a 86. And when you flip this, we have got the 82. So now we have to be conscious that when we should have, like when, like at which placeholder will put which value. Like first will be the actual value, and then will be the predicted value. So this is the correct way to use the R2 score functions. Right? Now, just like the classification, this isn't always what we want, right? So R2 score is of course a good matrix, right? But we also have the another method called MAPE, because this is a mean absolute percentage error, right? So earlier we have got the RMSE is an approximately $30,000. But now the question is the error of $30,000 acceptable? Like, let's say that we are selling our houses in terms of lakhs, right? And now we have the model error of 30,000. So now we do not know how much error, like we have to be compare every time that how much more, like how our model is making mistake. Like, are we making a mistake of at, so basically we want to know at what percentage our model is making mistake. And for that we can use the MAPE. So first we have got this RMSE, root mean square error, which is approximately 3000 error we have. Now the question is, so we have the error of 30,000. And the question is, if we have the house worth rupees 600,000 or 6 lakh, right? Now, if the house has the worth of 6 lakh, and then we have the error of 30,000, that is acceptable. So that is acceptable. That means here when you compare, then we can compare that there is a 5% error. Now we know that, like when we see in terms of percentage, it makes sense. But consider that if we have the house with worth of rupees 60,000, here we had the 600,000. Now we have the 60,000. So this error would be 50% error, and which is not acceptable, right? Like we are making a model with a 50% error. So we have to be understood, like we have to be sure that how much percentage error we are getting, right? And in our model, we have the both the cases. Here we can see that we have the model, which is the even the lower value, right? It so instead of 100,000, so maybe this is the even lower than the 100,000, right? And we have the extreme value, which is more than the 70, like 700,000, right? So we have the both scenario in our model, right? So now we want to know how much on an average our model is making percentage error, like how much on an average our model is making error in terms of percentage, right? So this is how our plot looks like, and we can clearly see that our model is kind of skewed, right? Now trust me, we do not want model trained on the skewed data. So we should always check whether our model, like whether our data is skewed or not, right? We have to make our data non-skewed every time. Now, how about looking at the percentage error? So here first we have created our, first we have got our predicted value. Then we are taking the difference of the predicted value divided by the actual value, and then multiplied with the 100. This will give me the percentage error. So here we have got the percentage error. So how do we get it? Basically the predicted value minus actual value, whatever the value we have got divided by the actual value, right? And again multiply with the 100, that will give you the percentage error. Now, there are both, like in the percentage error, we have the some negative percentage, we have some positive percentage, right? We can look at the absolute of this percentage, like absolute of the differences. So it doesn't matter whether we are whether we are predicting the lesser value or the higher value, but still we are making the error. So what we have done is, here we have made the absolute of the percentage. So we have taken the absolute of the percentage, and now this makes sense, right? Now this is what the MAP is, right? And after that we can take the mean of this, right? So for that we have created a function called MAP, which takes the true value and the predicted value and apply the first we take the differences and normalize it. Then we do the absolute, and then we take the mean of that, and then we multiply it with the 100, right? And after that, when we check it, here we can see that now we have the error of 10. That means we have made a 10% error. That means our model is making 10% error overall. This is saying, right? This is an overall 10% error we are making. Now, when we see the error in terms of percentage, now this makes sense, right? Like whenever you will try a model, you are likely to get 10% error, right? Maybe it will be 10% higher, or maybe it will be 10% lower. Okay. And this is interpretable, right? Now we have around 10% error, right? Now, sometimes we can also do is we can transform the target value, right? So when we do the fit method, so the question comes like, we care, like, does the fit, like this method care about the MAP function? No. So this, whenever we apply the fit method, it doesn't care about which function you are applying, right? So basically, so the question comes, why are we minimizing this MSC, right? Or a MAP. So when we minimize this mean squared error, right? So the expensive house will dominate because they are the biggest error. They have the biggest error. So that means when we minimize it, right? So because here we want to minimize it because only the expensive houses, right? And we have the very few expensive houses which will dominate the entire data set, which will dominate the entire error, right? We do not want that dominations. So the question comes is like, is the RMSE better? We cannot say that, right? And here, when we get the fit method, so how can we get fit method to think about MAP? That means when we apply the fit method, so we want to make our model so that when we apply the fit method, it will consider the MAP functions, right, during the consideration or during the learning, right? And the common practice that we do is to transform our target data. So we to is to like do the log transforming of the target data. So we have the y value, we want to do the log of y. So here this is the actual value without the transformation, and this is the after the transformation. So when we do the transformation of the log 10, we can see that now we have got the normalized output, right? Now we have the data which looks like a normal, which looks like it is coming from the normal distributions, right? And it is much better looking, right? Now, how do we incorporate our MAP functions into the target, into the fit method? Basically, we can use this transformed target regressor functions. It is being imported from the compose, right? Now here we are using this transform target regressor. In this, we are passing the ridge regression. We are passing the function as a log 1p. This will do the log transformation, right? And here we are also applying the inverse function as an exponential MP, right? Now this is our transform target regression. Now we can pass this. So now we can create a model with this preprocessor and the transform target regression, and then we apply fit and the predict. Right. Now when we try to check the MAP function after the prediction, we can see that now we have 7.8% error. So now we have the approximately 8% error. Earlier, our model was making 10% error, but now we have only 8% error, right? So now we have reduced the 2% of the error, which is a good, right? Now we can also apply the different scoring function with the cross validations, right? So instead of MSC, like here we can try the MSC instead of default R2 score. So when we apply the cross validation in the scoring attribute, we can pass the different function. Like here we are passing the negative mean squared error. This will be used the negative mean squared error functions, right? And yeah, and we can also, let's say that if you want to use map, so what we can do is this is the map function we have. We can use this make scorer function. Where is this make scorer? We have imported earlier. So like here this make map scorer has been imported earlier, right? So here we are using this map scorer. We are passing the map function and then we are saying greater is better, right? So this is the map function that we are doing. And now we are passing this map scorer function into the scoring. So basically all this technique is a way to incorporate a different functions rather than R2 score, right? And we can apply, and here when you look at the documentation of the scikit-learn, you will see that there are a lot of functions we have, right? And here we can see the test score and the trend score, right? We can also specify the list of this dictionary of the multiple scoring function. Like over here, we have created the dictionary of the multiple scoring function, and now we are passing that all that function. And when we look at the data, we can see that we have the output of all the scoring functions, right? We can again try to check the main function. Now we can also use regression matrix. So again we have already discussed about this negative mean square error, negative root mean square error. We have discussed about like, so again, like if you want to define your own scorer function, and if you do not want this interpretations, so you can set greater is better. That means this greater is better parameter to false. That means we are not interpreting this scorer function, right? There are a lot of things that we can do, right? And yeah, this is it. This is it for now, right? We have discussed about the like here we have discussed about the dummy classifier, like dummy regression, ridge regression, like read CV. We have discussed about a lot of scoring function like R2 score, map function, RMSE, and MSC function. All these functions we have discussed, right? Thank you very much.